Uh, good morning to all. In this class, we will solve some more problems uh, so that we can get clear picture or we can get even more clarity about the concepts which we have already learned in the previous classes. And also you can apply some formula and you can find out the problems. You can solve it very easily. So how to solve the problems? That is what we are going to discuss in this class. Okay, so for that we will take up a question. The question is, the equation for an AC voltage is given as, question is the the equation the equation for an AC voltage. For an AC voltage is given as, so he has given the instantaneous value of voltage waveform, and it is given by small letter v is equal to 0.04 sine 2000 t plus some 60 degree. Okay, determine the frequency. Determine the frequency f. Okay, f, frequency f. Then the angular frequency and instantaneous voltage when, and the instantaneous voltage when t equal to 160 ms microsecond. Okay, so that is what our problem. So the 60 degree is known as phase angle that we will learn in the next class. Okay, so for the time being you ignore the 60 degree. Okay, and we have the solution like this. So given, he has given that v is equal to vm sine omega t plus phi, which is the standard form of a sinusoidal voltage waveform, and that is equal to 0.04 sine 2000 t plus 60 degree. So this is our so on comparison we will get Vm is equal to 0.04 volt and omega will be equal to 2000. That means omega is nothing but 2 pi f, and right, 2 pi f radians per second. Omega is what do you mean by omega? Omega is nothing but your angular frequency. Okay, so if you don't know this omega, you go back to your previous class and learn it. Okay, so 2000, so 2 pi f will be equal to 2000 radian per second. So okay, and here, yes, he is asking determine the f, frequency f. So that means frequency F means the number of cycles per second, that is represented in hertz. Okay, so F will be equal to 2000 divided by 2 pi hertz. That means equal to, that will be equal to, we have calculator, okay, 2000 divided by 2 pi, okay, so that's equal to 318.3 hertz. That means 1 hertz means 1 cycle per second. That means 1 second, if you consider, you will get 1 cycle. That is what you mean by 1 hertz. So 318.3 hertz means that 318.3 number of cycles per second. 1 second, that means for 1 second you will get 318.3 number of cycles. Okay, yes, that means 318 number of full cycles and 0.3, that means 30% of the other cycle you will get it. So that is what do you mean by yes, frequency of the signal, of the waveform. Okay, then he is asking you to find out the angular frequency, that is nothing but 2 pi f. That on comparison you got the answer, it has 2 pi f equal to 2000 radians per second. So both solved. Okay, correctly we have solved it. So that's about our first question. Then yes, we have another question, that is he is also asking you to find out the instantaneous voltage value when t equal to 160 microsecond. So that means you have to put time t is equal to 160 microsecond here. Okay, that means, so V at t is equal to 160 microsecond, that will be equal to, so okay, that is equal to Vm, that is 0.04 sine 2000 into 160 into 10 power minus 6. Okay, minus 6 plus, so this is omega t. Actually this omega t is theta. Okay, theta equal to omega t, we know that. And this omega t is in radians per second, its unit, right? And t, unit of t is second. So second cancel. So this theta angle is always given in radian, not in degree. Okay, but in this case what happens is, we have the examiner has given 60 degree, so you cannot add degree with radian, two units. Okay, you have to if you have to add these two terms, then that two terms must be in same unit, either in degree or in radian. So you have to convert either degree in radian or radian in degree. So I am going to convert this 60 degree in radian. 60 degree in radian means pi by 6, not pi by 6, pi by 3. Okay, pi by 3. So pi by 3. So plus pi by 3 you will get it. Right. So that means we have the answer V at t equal to 160 microsecond. That's equal to, you just take your calculator and give this into your calculator and equate. Then you will get it as the answer will be answer is, I think, okay, this answer will be is 39.2 millivolt MV. M means milli, that means into 10 power minus 3. Okay, this is your answer. So that also we have done, that question also we have solved. So then we are moving on to our next problem. We are moving on to our next problem. For that, taking your previous year question paper, this, so no, this, no, yes, this waveform. Okay. Yes, question number 50. Determine the RMS and average value of the current waveform shown below for 10 marks. So I'm going to redraw this figure, okay, so that I should have two axes, x and y axis. So I think okay, this here I'm drawing. Okay. Yes. Yes, this is my x-axis, and along x-axis we have t, time in second, right? Time in a second, yes. And we have I of t y-axis. On y-axis we have I of t. That means it is a current waveform. Okay, and the waveform looks like this. Yes, 0, 2, 4, 6, like that. That means when it is 0 and 2, then 4, then I have 6, then I have 8. And 0 to 2, I have a waveform like this. Okay, I have a waveform like this. And 2 to 4, I have a waveform like this. Okay, and again, I have from 4 to 6, I have waveform like linear graph. And again, I have this. Okay, this is our waveform looks like, and the examiner also given the peak value in the positive half as well as in the negative half. It is given as it is here. This is plus 10 ampere, and on the negative half I have minus 10 ampere. So this is our problem. So you have to find out the IRMS value. IRMS is equal to dash ampere, and I average equal to dash ampere. So these are the two values you have to find out. So I'm applying the, first of all I am finding out the average value. Average value means I have the formula is average value. I average is equal to area of one cycle divided by length of one cycle. Okay, so in this case it will be equal to area of one cycle. It will be one cycle means, if you observe this waveform, it is the waveform is got repeated after the 4th second. That means 0 to 4th second the waveform is like this, and 4 to 8 the waveform, the same waveform is repeated, right? So that means I have yes, the length of one cycle as 4 second. That means t, time period t is equal to 4 second. Okay, and area I have a1 and a2. Okay, and so the total area will be, so the formula will be a1, okay, a1, okay, plus a2 divided by length of one cycle, that is t, that is time period of waveform. Okay, and that is equal to a1 is equal to, a1 is nothing but your a triangle, right? So the area of a triangle will be half bh, half b into h, that's equal to half into b is this is b, and h is this. So half into b is 2 into h is 10, so it will be equal to 10 plus 10, and a2 is equal to a2 is nothing but a rectangle. Okay, so two side L into length into breadth, you will get the area of the rectangle. So length is again 2, and the width is actually minus 10. That means actually this, yes, this is your width and this is your length. So that means 2 to 4, that is 4 minus 2, 2 you will get, and peak value is minus 10, so width will be minus 10. So A2 will be equal to minus 20. Okay, so average value I average is equal to A1 plus A2, that is 10 plus minus 20 divided by T, that is 4. That's equal to minus 10 by 4, that is equal to 10 by 2, 5 by 2, so 2.5 minus 2.5. Right, so our average value will be negative value, a negative value, and that means if it looks like this, minus 2.5 means like this. This is our average value, minus 2.5 ampere. Okay, now I'm how to find out the RMS value. Okay, RMS value. So in order to get the RMS value, we have this I of t. Okay, and I of t, I have to model this I of t in two intervals. From 0 to 2, it is having one look, and from 2 to 4, it is having another look. So I have to model, or I have to mathematically define what is actually I of t. So I of t is equal to, that means two functions from 0 less than or equal to t less than or equal to 2, and another function from 2 less than or equal to t less than or equal to 4. Okay, and from 2 to 4, it is very clear that it is minus 10. Right, now from 0 to 2, I have a function, a linear function, a straight line. Okay, and 0 0 is its first point, and I have 2 10 as my second point. So if you have 2 points of if you know the 2 points in a straight line, then you can find out the equation of the straight line, right? So that is given by y minus y1 by x minus x1 equal to y2 minus y1 by x2 minus x1. So y minus y1, that is, this is x1 y1 and this is x2 y2. So y minus y1 means y minus 0 divided by x minus 0 equal to y2 minus y1 by x2 minus x1. 10 minus 0 divided by 2 minus 0. Okay, that means y is equal to 5x. Okay, so in this case, x-axis is time t, and along y-axis it is I of t. So I am replacing y and x by I of t and x with a t. Then I of t equal to 5t is our equation. Okay, so I of t is defined in two intervals like this, 5t and minus 10. Okay, now you can calculate, you can Okay, I'm taking this I of tm. I have to select this I of t. Okay, anyway, yes, I of t equal to 510 minus 10. Now I have to find out the RMS value. Yes, RMS value. I have yes, RMS equal to formula square root of integral I square dt, okay, I square dt divided by length of one cycle, that is t. Okay, and so here it will be, yes, I'm defining this I integral I square dt will be equal to, I have to split it in two intervals. So two integrals will be there. So integral 0 to 2 I because I of t is defined for two intervals in two manner, 5t and minus 10. So you have to split the integration. So integral 0 to 2 I square dt plus integral 2 to 4 I square dt. Okay, so that will be equal to integral 0 to 2 I of t is 5t square dt plus integral 2 to 4 I square dt is minus 10 square dt. Okay, so I will get 25 integral 0 to 2 t square dt plus 100 integral 2 to 4 k dt. So that will be equal to 25 into t square dt is 2t cube by 3 0 2 plus 100 into t 2 4 2 to 4 0 to 2. Okay, so my integral I square dt will be equal to 25 by 3 t cube means 8 minus 0 plus 100 into 4 minus 2, that is 2. Okay, that's equal to 25 into 8 by 3 plus 200. Okay, so that means, so this is what our integral I square dt. Okay, so I'm taking it as 1. So I'm substituting this 1 in in A. This is A. So I'm substituting 1 in A. Okay, so what happens? And also we have capital T, that is what I mean by time period. Time period is nothing but 4 seconds, right? So I have RMS value. Okay, RMS value I have IRMS equals to, okay, that means IRMS will be equal to 1 by 4, right? 1 by 4 into integral I square dt is this. Yes, this one. Sorry. Okay, 25 into 8. Okay, that means 200 by 3 plus 200. Okay, so I'm substituting the here 200 by 3 plus 200. Okay, and this is actually I'm squaring on both sides. So on squaring both sides, the root square root will disappear. So IRMS square will be equal to this one. So that's equal to, that will be equal to 1 by 4 into 200. That means 5, 50. Okay, 50 by 3 plus I have 50, and that's equal to, yes, 50 by 3. So 150, 200 by 3 I will get. So that will be equal to, so IRMS value will be equal to under root 200 by 3 ampere. Okay, this is about what I mean by, yes, RMS value. Okay, now I'm going to define the peak factor and form factor for this waveform. Actually, for any kind of waveform, any figure, okay, it is not only a sinusoidal waveform, not only sinusoidal. For any waveform, you can define form factor as well as peak factor. Form factor and peak factor. So I'm defining here the form factor and peak factor for this case. That is, form factor will be a form factor. By definition, it is equal to Kf equal to, by definition, it is equal to RMS value divided by average value. Okay, so that will be equal to minus 2.5, right? Okay, it will be equal to RMS value is under root 200 by 3 divided by minus 2.5. So this is our form factor, and peak factor equal to Kp. Okay, and it is defined as the ratio of RMS value, ratio of peak value to the RMS value. That is peak value divided by RMS value. That is equal to, peak value is 10 divided by, okay, RMS value is under root 200 by 3. So this will be your peak factor. Okay, so form factor. So peak factor is also known as crust factor. Also, crust factor. Why? Because for another name of peak is crest. Okay, crest factor. So that is also done. Okay, now we have solved almost all kind of problems, right? So what we will do the next section is that we will move on to our next module. That is module 3. Okay, for before getting into the entering into this module 3, we have to clear some concepts. Okay, some concepts called phases. Phasor. What do you mean by a phasor? Okay, this phasor. So for that, we have to physically model a sinusoidal waveform. That means physical model for a sinusoid function. So why? Because in module 3 we will be only discussing about the sinusoidal waveforms. Sinusoidal waveforms means in general sine and cosine, sine and cos functions. That means sine omega t as well as cos omega t we will be dealing with. Okay, so sine omega t, cos omega t, these two are known as the sinusoid functions in general. Okay, so you have to have a physical model for sinusoid functions. So that means what is exactly a sinusoidal function? Okay, so this sinusoidal waveform, okay, for an AC voltage, by you can get a sinusoidal waveform for an AC voltage by imagining a crank, a bar, or a rod. Okay, or a rod. That rod is rotating in counterclockwise direction, that is in anti-clockwise direction, about point A with a uniform angular speed omega. So that describes physically what you mean by a sinusoid function. So that means let me consider this figure. Yes, let me consider a circle first of all. Okay. No, this is okay. Now I am going to a sinusoid circle. Okay, like as shown in this here we have spaces like this. Yes, physical model. Yes, this figure I'm taking. Okay, this figure. Okay, here. Yes, this figure. Let me consider this figure. Okay, yes, in this figure, I have a crank like this. This is my crank. AB is my crank or rod. Okay, and this is fixed. This rod is fixed at point A, and it is free to rotate in anti-clockwise direction. That is in counterclockwise direction. That is in this direction. In this, sorry, in this direction, like this, right? So in that case, the sinusoidal function, that is sinusoidal waveform, is nothing but its projection. The projection of the tip of this rod, that is the point B. If you project that point B on the uh, y-axis, okay, on the y-axis, then uh, you will get the sinusoidal function. That means this let us consider a time instant t1. Okay, t1. At t1, the position of this crank or rod is like this. Okay, so that means this sinusoidal waveform, if you project sinusoidal, sorry, not sinusoidal, if you project this point B, that is tip of the rod B, on this y-axis, okay, y-axis, then you will get the corresponding sinusoidal value here. The corresponding sinusoidal value. That means this length, the vertical length corresponding to this projected length, gives the corresponding sinusoidal value at this instant of time, t1. Okay, and similarly at theta, okay, this is time. We have considered the time t equal to t1. When you are considering the angular angle, okay, then you have to just multiply with omega. So omega t and omega t1. So that will be equal to theta 1 and theta. Okay. So let theta 1, or sorry, let theta equal to pi by 2. Then theta equal to pi by 2 means sinusoidal function is having the peak value, that is Vm, right? So at the same time, theta equal to pi by 2 means, yes, this rod, this crank or this rod is rotated through an angle 90 degree with this axis, this positive x-axis. It is rotated through an angle 90 degree like this, so that the B point B will be here, will reach here at this point B, so that the projection will be projection of that point on this y-axis will be that point itself. Okay, that point itself. That means it will give the maximum value. That means nowhere on this circle it will give this maximum point peak value. Okay, that means if you consider point B here, or point B here, point B here, point B here, then on projecting these points on y-axis, then that projection, that vertical, all such vertical lengths must be less than this B, this AB value. So that means it will be corresponding to the peak value. Okay, that means this crank or this rod is rotated through an angle theta equal to 90 degree. Okay, if you rotate it through 90 degree, then that corresponds to the sinusoidal the value of the sinusoidal function at theta equal to pi by 2, So that means as the sinusoidal waveform is increasing from 0 to pi by 2, increasing from 0 to Vm, actually 0 to Vm, that is peak value, then this crank, this rod, or in other ways this is known as the phaser, and this phaser is rotating from 0 angle, that is theta equal to 0, to theta equal to 90 degree or pi by 2 radian. Okay, yes, that is the meaning. So then sinusoidal waveform is decreasing from Vm to 0 again. So in that time interval, or in that angle period, the phasor will be rotating from theta equal to 90 degree to theta equal to pi degree. So the phasor at theta equal to pi will be like this: B, A, B, like this. So as the sinusoidal waveform, let it be small letter v, as this v completes one full cycle. Okay, one full cycle, that means it increases positively and decreases in the positive half cycle, and it increases towards the negative and decreases towards the 0. And as this happens, as this happens, this rod or the phasor is rotating with an angular frequency omega, or with a speed, angular speed or angular velocity omega, from theta equal to 0, that is coinciding with the x-axis, and it is rotating in counterclockwise direction, that is anti-clockwise direction, from theta equal to 0 to theta equal to 2 pi, or theta equal to 360 degree. Okay, so and after 2 pi the waveform is got repeated like this. Okay, then what happens to our phasor? Then phasor also will repeat the rotation from 0 to 2 pi again. It will rotate in anti-clockwise direction. Okay, so that is what is the physical meaning of sinusoidal waveform. Okay, or sine waveform. or similarly you can model the cosine waveform also. Okay, in that situation it will be projected and will be projected this phasor will be starting from this y-axis, positive y-axis, plus y, and this is minus y. So the phasor at theta equal to 0 for cosine function, it will start from positive y-axis. That means the phasor start from positive y-axis. Okay. Yes. So yes. Now I would like to introduce a new terminology known as, or a new concept known as phasor. Phasor. So what I mean by phasor is this. The phasor is nothing but your rod crank. Okay, the rotating magnitude, rotating rod. So that is what you call it as phasor. Now I have another concept known as phase difference. Phase difference. So I have already said that if you are considering, if you are modeling the cosine function, then the phasor should start from the positive y-axis. That means it, first of all, it will coincide with the positive y-axis, and as the waveform advances from 0 to its time period, then the phasor will advance in what, counterclockwise direction or anti-clockwise direction, starting from positive y-axis. Okay, that is what the cosine function will look can be modeled. So with the same provided that the same angular frequency omega. So the speed, the angular speed or the angular velocity with which the phasor or the rod is rotating is known as the angular frequency. Okay, angular frequency omega or angular velocity omega. Okay, so in our discussion, the sine and cosine waveforms, these two waveforms are rotating in the rotating with the same angular frequency omega. Okay, so at that instant, so sorry, at that point of, so in this case, at any point of time you will take, okay, at any point of time you take, okay, at any point of time means let theta equal to theta 1 be any arbitrary angle. Okay, at theta equal to theta 1, if you consider, okay, then this sine and cosine waveforms will be having a phase difference of 90 degree always. For example, let theta 1 equal to 0. Theta 1 equal to 0, at theta 1 equal to 0, the sine waveform, the sine function starts from this positive x-axis, like this. This is our phasor, right? Then at the same theta 1, that is theta 1 equal to 0, the cosine waveform, the cos function starts from the positive y-axis, like this, right? So if you take a snapshot at this instant, if you have a camera and if you take a snapshot at this instant, right, then your phasor, the two phasor looks like this, and these two faces are the angle between these two faces is 90 degree. Okay, yes, that is what do you mean by this angle is known as the phase angle or phase angle difference. Okay, and it is denoted by phi. Okay, here phi is equal to 90 degree. I can prove this concept in another way also. How to prove is that I can have I know in maths I know. Okay. Yes, in maths I know sine theta equal to cos 90 minus theta, right? 90 minus theta, or cos theta is equal to sine 90 minus theta. Okay, this is my what? Yes, this is my relation in mathematics. And also you can write cos theta is equal to sine 90 plus theta also, right? That is equal to sine theta plus 90, you can say. That means cos theta equal to sine theta plus 90. That means the phase angle difference is phi is equal to 90 degree between cos theta function and sine theta function. Okay, plus 90 degree. That means this cos function is cos in other words. We will the electrical engineers will say the cos function is leading by an angle plus 90 degree. Okay, or in other words, the cos, that means cos function is a little bit earlier. Okay, leading means earlier, appearing earlier by an angle plus 90 degree with respect to sine waveform. Okay, that is our meaning. Okay, or in other words, you can say this. You can understand this words or this concept in another way also. The cos function is leading, or you can say the sine function is lagging, or you can say lagging means coming or appearing late, is lagging by 90 degree with respect to our cos function. Okay, yes, this is the meaning of phasor. So we have completed what do you mean by phasor. Okay. Okay, what do you mean by phasor? Then what do you mean by phase angle? Then also we have covered what do you mean by phase angle difference. Okay, and also we have covered what do you mean by lagging phase angle. Then also leading phase angle. What do you mean by leading phase angle? Okay, so all these terms are, or the concepts are very important in electrical engineering. Okay, yes, so we will stop here. So thank you so much.